Greetings. Today's lab is an analysis of the motion of an object that falls less rapidly than a stone and of the force or forces that act on it. It will work well to expand our ability to use Python to make more complex predictions as well. The problem, the source, the goal of our work is to analytically explain why our object falls less quickly than it would if acted on only by the gravitational pull of the Earth. With that information, we're to modify the code of our Python model until its prediction aligns with our actual data. The physics model itself, it returns us to Newton's second law that links the net force on an object to its change in velocity, its acceleration, if you will. The force of gravity pulls down on the object towards the center of the Earth. The acceleration caused by gravity alone is 9.81 meters per second down toward the center of the Earth. The experimental setup is to be described in the next few pictures. The notion is to demonstrate to you the efforts that were made to maintain as little angular distortion as possible, why the meter stick, so-called, is calibrated at 0.9985 meters, and why, and the next piece is to show you the actual object, quickly followed by the very brief motion that is being analyzed, 0.7 seconds. The items listed in detail here include some of the code which was changed, partially in the beginning and other parts when it was found that the actual motion did not correspond to the initial prediction. All of the changes are noted here. Here's the tracker data. The tracker data is based, of course, on the observation, and to the right you see a graph of the data, and you see the tabular representation of it as well. It will be moved to Excel to compare with the Python prediction briefly. Here are the code pages that were created both before and after the analysis, and you can stop this and see any pieces of it that you would like to see. Here we have the data, the actual data. The red data notes what Python predicted, and the blue data, what really happened. The actual tracked video did not move as far in the same time as the predicted graph of the Python data showed. Why was that? We anticipated that they would be different, misaligned, if you will. It's concluded that a drag force will shrink that divergence, and the code and model were extended as shown here to compensate for it, shown particularly at the bottom of the page with respect to the model, and on the following brief slide concerning the Python modifications. Here you see the graph afterwards, and the expected change in achieving better agreement in data is seen in the graph of these modified Python prediction data points, which are the red ones. Inclusion of the drag force does not remove all error sources. We still have issues concerning our ability to mark tracker accurately. The camera positioning was careful, but it was not foolproof, and further relationships with velocity remain to be made. In conclusion, we note that a falling object subject to the gravitational attraction of the Earth may also experience the action of other, especially invisible forces that affect its motion. Small, smooth objects are affected very little, but larger, lighter, floatier objects must be considered with regard to the upward drag force. Building prediction models must include considering evidence from actual observations. I thank you for working this through with me.